At the very end of the episode, we see Juliet go from the bottom of the silo up to the top, and she does this
Yep.
panicky swim. But I don't think she needed to. I mean, people panic, but I think if she came up slowly, it would have been totally fine.
Okay.
She took off her boots. I think it's to be lighter. I think.
Okay.
Pull on the rope. Makes sense.
Okay.
But then the rope goes slack. She starts panicking.
Okay. So for me, this made a lot of sense to me. She's only once the air goes out, she's got to go like 100 meters up to the surface. She only has the air in her lungs. That's not going to last, right?
I think it does.
It does.
Well, let's watch her. She like reaches the surface and she's gasping for air.
Yeah. So that's what I'm saying. Is like she's grasping for air because she only had the air in her lungs. She's got to get to the surface to get to the air, right?
So I'm not a deep sea diving person, but from what I've heard and read, I think it's not like that. It's as long as you don't panic, you're okay. And so I did this calculation, a rough calculation, conceptually. So if you're at the bottom of the ocean, you're like this crab on the bottom of the seafloor, you get pulled up rapidly, right? And to the surface, you undergo a very large pressure change. And so this, you want to come up slowly for one reason is because you don't want the nitrogen to dissolve into your bloodstream, then work its way up to your brain. Now you have a part of your brain that's not getting blood flow, then you die. Okay, but I think if you come up slowly, you're fine. And so first, let's, I guess, step by step this. So if you're in the boat at the top of this water column, and if you went down, you would get an increase in water pressure.
Okay.
And so we can see that from equation number 1 there. That's Bernoulli's equation. This is for fluid flow. And so we have, it's really an energy density equation. You take the energy in an area, and then you divide by volume, you get energy density, which for pressure, which is pressure, is a type of energy density. The second term is for kinetic energy. The third term is for potential energy from gravity. And then the fourth term on the right side of the equation is energy losses due to thermal losses. Now, if we go from a straight vertical column, we don't have to worry about the speed of the water. We don't have to worry about energy losses. So we can cross out those two terms. We get the change in pressure is equal to minus the water density times the gravitational acceleration g times the change in height. All of that is to say, when you go down in water, you get an increase in pressure. Okay, so can you put your mouse on a column of water right next to the air hose?
Okay, so like
so we're talking about coming from the atmosphere, exactly, from the atmosphere down to the water hose.
Right.
If we go to the side and see where that air hose and the water meet up, these pressures have to be the same.
Right? Have to be the same
because they have to be in equilibrium. If the pressure inside the air hose was less than the pressure in the water, then the pressure in the water would push the air hose, push the water level in the air hose up.
Agreed.
Okay, so that is to say that if you're water, you come down every 10 meters is an additional atmosphere. So if you're down 50 meters, you're now down at 6 ATM, the one atmosphere from the air, and one more for every 10 meters. That also means that the pressure in the air hose right at the bottom is also, what did I say, 5 ATM?
6 ATM.
What?
So 5
6
50 meters
ATM.
down, so 6 ATM total.
Exactly. So the pressure of the gas in the air hose right there is 6 times the pressure. Okay, now let's move over to the ideal gas law. PV equals N kBT. Pressure times the volume is equal to the total number of atoms times this Boltzmann constant, 6.62 times 1.3 times 10 to the negative 23 J per K times the temperature. Okay, so if we consider the volume as the volume of what's her name?
Juliet.
Juliet, yeah, thank you. The volume of Juliet's lungs, that volume is the same. So whether she's at the top at the boat or down at the bottom, the size of her lungs, they expand a little bit, but they're not like expanding meters. Okay, so how can we get a gas pressure down at that depth to be 6 atm? Well, you increase the number of gas particles n.
Okay.
So
So let me.
what
Can I walk through this a
yeah,
second?
yeah, yeah, yeah,
So
yeah.
when Juliet's at the very bottom, she's
Mm-hmm.
breathing through the hose,
Yep.
and since she's at high pressure down in the water, the air hose air down at the bottom must be at the same pressure,
Exactly.
and so she can breathe through it.
Right.
And then we're going to look at the amount of air in her lungs. We can use the ideal gas law and say the pressure is now super high when she's down, way
Mm-hmm.
down in the water. And because the volume of her lungs doesn't change that much and the temperature doesn't change that much, and
Mm-hmm.
Boltzmann's constant is a constant, the only way to get high pressure is to increase the number of atoms.
That's right.
Which means if she's at like 6 atmospheres, then she has 5 times the number of atoms in her
Six
lungs.
times. 6 times. Yeah, yeah.
Well, five times, right?
Five additional more than the usual.
Right. So that's right. So if it's 1 N at atmosphere, she now has at 6 atmospheres she'll have six times. Six times that. Five
Right.
additional. And
Right.
so the pressure in her lungs is super high, entirely due to the new atoms, the additional
Right.
atoms in her lungs. So if you
Or
only
another, maybe like an
Go ahead.
easy way to say it is if you
Mhm.
take a breath down deep, it's the same as
Yeah.
taking 6 times the amount of gas as if you were up at the top.
Okay. Okay. So in the clip, she's down here. The air
Right.
hose goes away. She
Yep.
loses pressure. And now she's down at the bottom here with a huge amount of oxygen in her lungs.
What
Uh,
one lungs full, one volume,
Mm.
but it's actually very dense. There's 6 times the amount of gas, or however much. There's a
Yeah.
lot more gas than there usually is.
Right.
And so I think it's enough oxygen for her to make it up.
Yeah.
As long
So
as she
if you
comes up slowly.
Yeah. So if you're saying if I hold my breath, I can hold my breath for a minute
Okay.
at up here. If I take one big breath and hold my breath down here, I now have 6 times that. So it's 6 minutes.
Right.
And the lower I go, the more time I get to hold my breath.
And so the coming up slow, the reason you want to come up slow is so that you don't dissolve the nitrogen gas in your bloodstream that's dissolved. You don't want wait, how do I say this? You want to take the nitrogen that's in your gas into your bloodstream. You don't want it to form bubbles. So you come
Right.
up slowly. Another reason you come up slowly is is that you're coming up calmly with very like minimal physical exertion, because
Mhm.
your body, that way your body can use the same amount of oxygen like per second. Why is that
Right.
important? Because then you're generating like a very small amount of carbon dioxide. Like my understanding of people's that burning sensation when you hold your breath for too long, it's not actually that you're out of oxygen. It's that the carbon dioxide that you're exhaling, that you're generating, is turning into carboxylic acid and it's burning, and so then you get a burning feeling and your body's like, get it out, get it out, get it out. Okay, but if you stay calm, then you don't have an accelerated consumption of oxygen. You don't have a accelerated generation of carbon dioxide. And then since you have so much gas in your body because you inhaled this high pressure air, then that amount of carbon dioxide that you generate is actually a small percentage, or at least
Yeah.
smaller than you would have if you had come up, if you're at the surface.
I see.
So I think
So-
she would have had enough oxygen.
So what you're saying is what she should have done is realize at the bottom here she has plenty. She has lots of time because she has
Yep.
so much air in her lungs. So she just go up maybe 10 meters, exhale a little
Chill
bit,
out.
chill out for a little bit,
Right.
and then maybe do a Valsalva thing, and then this is the equilibrate with your ears, you know.
Oh, okay. Yeah,
Yeah.
yeah, yeah.
And then go up another 10 meters, chill out, release
Mhm,
some
mhm.
air, and do the same thing, and just step by step up there. And she could have up to, it looks like she's really far down in the water. She could
Right.
have up to like 5 to 10 minutes to do this.
I don't have any numbers on that, but from
Right.
what I've heard from deep sea divers, and I guess not as deep sea divers, that like free divers, that
Yeah.
you actually have a lot of air in your body.
Yeah, that's
Like, as
wild.
long as you know about it and you know not to panic, it's okay.
Yeah.
And I'm glad you said there in your example and in your explanation is that you have to let out some gas as you go. Like even though there's still good oxygen in there, if you hold your breath the whole way, then your lungs will expand as the pressure equilibrates. So you have to let
Right.
out some air.
Right. I guess it might actually get painful where you're like, I gotta exhale as you go up.
Right.
that
But
it might
not
be
because of the
natural.
burning from carbon dioxide, but
Right.
because there's just your lungs are too expanded and it's like
Right.
too much pressure.
Right. So in the scene, I thought she panicked because she ran out of oxygen, and so she's like, "I'm gonna screw the bends. I'm just gonna
Up the
go."
top. Go, go, go. Yep.
But actually, she's got so much air in her lungs, she doesn't have to go that quickly.
Right. I mean,
Okay.
but as long as you can stay calm, which like like not an easy thing, like for sure.
Right.
Like I've never been in that situation. I
Right.
probably would panic too. But if she could push past that, I think the rise to the top is actually very comfortable.
Right. I think one big thing about not panicking would be knowing that you have time.
Right.
If she doesn't know it, then she's going to panic thinking she doesn't have time.
I don't want to drown.
I don't want to drown.
Right.
Yeah. Yeah. And at the very end, she did something that really annoyed me.
Oh?
She threw the goggles away. Watch. She's got the goggles with the flashlight attached. She throws them away. They're not in her hand anymore.
Yeah, those are not going to be made again. Those are the last goggles ever.
I mean, I guess Solo kind of put them together, improvised with a welding suit or something, and but what are you doing? You might need to go into the water again.
I didn't mean it sarcastically. I mean, like, how many sets of welding goggles does you have?
That's right.
How many sets of perfectly cut glasses you have? Like, unless they're manufacturing rubber to adapt to any size glass, like, no. This is maybe the last one that they're ever going to see. She like threw it away.
Why? Okay. In episode 1, she threw away the plastic container that rescued her when she fell in the water. She's got a second plastic container because this one's red.
That's right. That's the different one.
Yeah.
I noticed that too.
We got a screenshot from the first episode. Here she is. She was rescued by this plastic container.
Yep.
Definitely gray. This one is clearly red.
Maybe this is actually a lesson of this is a good place to keep them. Because you never know when you might be in the water again. So you keep your containers, your flotation devices floating on the water.
And they're just doing some work. I mean, they're just ready for flotation and rescuing at all times.
This is the end. This saved the series twice. These floating containers.
But the thing about the goggles, though, is the goggles don't float. They're sinking to the bottom of the silo. They're gone forever. You're never going to get them back.
That's right.
And might need to go back into the water.
Oh, she have to swim all the way to the bottom. What if she can't find a proper helmet? This could have been useful. Like a proper helmet for when she wants to leave this silo. This could have been useful for her. It's not like airtight to her mouth, but at least it covers her eyes and stuff.
Right, so she couldn't find a full helmet, but she could have goggles plus an air mask.
A little air mask. That'll do it.
But without the goggles, maybe it'll burn her eyes. She can't see when she goes outside. It's just so many reasons to keep the goggles.
Yeah, and why did she even need to pull them off? Right? It's not like the water was in her eyes or anything.
That's right. Get secure on the stairs before you pull them off.
Yep.
And then take them off. I mean, it's a
flashlight.
situation.
There's a flashlight built into those. She threw away a flashlight too.
Right. There's a flashlight. Yeah. It's a working flashlight, and it's working so well that it went down to super high pressures and came back up. So it's a solid flashlight. Gone.
Honestly, if I was Solo, I'd be pissed. I made this thing for you. Threw it away. Threw it down to this bottom of the water that we'll never see again.
Yeah. I thought you wanted to go to a different silo, and now you're throwing away good equipment. Juliet.
Ah, Juliet. But she aced this entire excursion. Like, she didn't have any problems other than Solo disappearing.
That's not her fault. We think because somebody else is in the silo and he got stabbed or something.
Looks like it.
Looks like it. We'll find out next time.
Nosebleed. Had to run.
All right, we'll find out. Season 2, episode 7, next time.